Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference. Parallel and distributed analytics applied to transport and logistics chains. Sparse analytics or parallel and distributed analytics. There are two approaches to process data from a super measurement system that provides a non-enumerating amount of data in real time and asynchronously: parallel analytics and distributed analytics. These two terms seem to be the same, but they are different and complementary terms. The parallelism and distribution of computing processing goes beyond the simple construction of parallel mathematical algorithms. It implies a way of facing problems with the bottom-up approach, from the description of atoms to integrating the vision of the entire system. It is a way of thinking about mathematics, according to the development of computer technologies. This is consistent with the abolition of monolithic computer applications, to make way for distributed applications based on microservices. Then the next step of advanced analytics is sparse analytics, which is based on parallel and distributed analytics. Asynchronous parallel analytics, called asynchronous parallel optimization by Velasquez, in 1995, 1997, and 1998, is defined as the act of solving a mathematical problem, using multiple cores on a computer, or on a computer grid, using modern multiprocessing environments, uniting the theories of decomposition and partition of large systems, that allow to structure complex multi-level mathematical models. Parallel analytics distributes workloads for data analysis, across multiple nodes in a server cluster, rather than addressing a large problem on a single supernode. The algorithms run on each node, processing a subset of the data. When processing is complete, or whenever required, datasets are aggregated, or rejoined, to generate collective information. There are many advantages of the asynchronous parallel approach. Less time to get information. By putting multiple nodes to work on the same problem, you can get insights from the data much more quickly than would be possible by running an analytics application on a single supernode with linear processing. This is a huge benefit when you want to get quick responses from massive amounts of data, and asynchronous processing allows to produce information that can be stored in memory until it is required by some subproblem. This speeds up the solution. In addition, it requires less demand for resources, avoiding congestion in computer systems. Distributed analytics is based on parallel analytics, and it is the distribution of the mathematical modeling process in many agents that act simultaneous and independently when they received information from its exogenous environment. The process can be summarized in the following steps. From a top-down process analysis, it is possible to construct mathematical or logical rules of interaction between multiple agents, representing each one a part of the system. Jointly, all the agents can represent the state of the reality. Starting from math or logic rules, following an approach bottom-up, it is possible to build segmented or atomized models of the real world. Using asynchronous parallel processing, it is possible to define the simultaneous actions of all agents that keep on the right path a cyber-physical system. This processing is different from the traditional one, based on the synchronized use of mathematical models that are executed periodically. Autonomous real-time distributed optimization. Mathematically, this process may be supported by large-scale optimization algorithms aimed at solving very large optimization mathematical problems, based on the intensive use of methodologies for partitioning and decomposition of systems. New technologies and big data shift from traditional optimization based on synchronized moments to modern optimization based on real-time events, in which models will run autonomously, when necessary, by events. Autonomous real-time distributed analytics is a topic open to researchers in advanced analytics. Artificial brains is a disruptive modeling methodologies for Industry 4.0, based on the integration of artificial intelligence and mathematical programming. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, The artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. The decision support systems, DSS, were conceptualized as a set of mathematical models that exchange information between them, working offline. The artificial brain is the evolution of DSS under the Industry 4.0 revolution, that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. So, the artificial hypothalamus, a part of the artificial brain, is the algorithm that control the workflow of the models of the decision support system. It includes a general math language between algorithms that guarantees that the system is in the optimal path. This is based on the duality theory. In real-time and uncertain systems, the concept of an optimal point must be replaced by that of optimal path, as the one who is always close to the ideal optimal points. The algorithm that simulates the hypothalamus is assembled by Optex, the HI's artificial intelligence, to generate mathematical programming solutions, using the models that traditionally make up a decision support system. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. Autonomous real-time routing and distributed optimization. Industry 4.0 real-time routing. Challenge: modify the traditional vehicle routing process to access to the Industry 4.0 environment. Solution: it implies that all agents, the dispatcher and the vehicles, need to know what information they need to take from smart metering systems, and what information they need to provide to other agents to make their decisions, to keep the system end-to-end on the path to optimality. This is possible using asynchronous parallel optimization methodologies. In the case of freight transport, the traditional process of planning logistics operations in a city could be carried out as follows. At the end of a period, for example, a day, or a shift, a dispatcher plans all routes to fulfill the deliveries or pickups of the next period. This may involve solving the problem of routing vehicles with time windows on customers, optimizing an objective function according to the company's business rules. Even for small fleets of vehicles, this is a complex mathematical problem, when we consider all the limitations in real systems. The dispatcher generates the route, the sequence of clients, and possibly the sequence of streets, for each vehicle that will be used that period. This schedule is fixed, and it may be considering static travel times for the entire period. That is not true. At the end of the period, the dispatcher updates the database considering the contingencies that occurred during the period, and will start the process again. Given the reality of the process, in which travel times are uncertain, and change dynamically during the period, the programming carried out cannot be optimal. To transit the path of optimality, a dynamic scheduling can use all the power offered by smart metering systems, like Waze, which, in any time, provides rich information for each truck. The best path, or a route close to the best, and a good forecast of the actual travel time. Additionally, it may be possible to obtain historical data on travel times, differentiated by time of day, day of the week of the month, etc. This allows the dispatcher to have up-to-date information to solve a vehicle route issue with time-dependent time and travel time windows, which should produce better results. The dispatch process can be adjusted as follows. At a certain point in the period, the dispatcher plans all routes solving the routing problem with time windows and time-dependent travel time, taking as input data the latest database updated by all smart metering systems, that is, the trucks, Waze, hydroclimatological, and traffic databases. This process would be carried out centrally, to generate a forecast of the route of each vehicle, to be used that day. Each route must be uploaded to MSD, a mobile smart device, such as a Raspberry computer, VDO, iPhone, or iPad, through which data is received from a SM, a smart metering system, such as Waze. During the route, at the end of service on a client, the MSD mobile device asks SM for information about the estimated travel times and optimal routes to complete the route. With the new information, the MSD can solve a TSP, travel salesman problem, to recalculate the optimal missing route, that is customer service order, and attention times. MSD send that information to the dispatcher, so that, if necessary, it will rearrange the planning of all routes. The approach may be conceived as an artificial brain composed of a network of mathematical models, the VRP dispatcher, TSP problems in trucks, and the mathematical models provided by Waze, and the existing measurement systems. The communication between the algorithms of mathematical problems must be asynchronous, since events occur in the system. Two levels of interconnection can be visualized, with the dispatcher, to coordinate the entire system, and between trucks, to improve truck decisions. To establish the communication protocol between agents, the decoupled view of a routing problem can be considered, which may be solved using Bender's theory, Lagrangian relaxation, column generation, or cross-decomposition. These methodologies already include math communication between algorithms, to improve the solution of the integral optimization problem. Autonomous real-time energy optimization. Fuel consumption can account for up to 63.9% of the variable operating costs of a heavy ground transport fleet, therefore, it is a critical factor in the planning and scheduling of truck routes. In state-of-the-art cargo transport vehicles, the engines are electronic, digitally controlled, with telemetry capability of the nearby environment that optimizes fuel efficiency. This autonomous capability of modern vehicles can be called optimal short-range control. There is another level of operations planning of a fleet of vehicles that is long-range, and that must contemplate the full route of the vehicle, and the planned times of arrival. The importance of this planning is seen in the performance curve of an engine in which operating in a range of 1,100 to 2,000 revolutions per minute results in optimal performance between 1,500 and 1,800 RPM, according to the truck's provider. However, optimal power performance, with lower fuel consumption, is below 1,500 revolutions per minute. As in any vehicle, the compromise between speed and economy do not move in the same direction. So, optimizing energy consumption is complex because the consumption function is not linear and depends on factors that are the result of decision-making, such as vehicle charging and geoposition. Route-dependent factors, which can be divided into static, for example, slope, roughness, and dynamic, for example, traffic, route weather. While the mathematical problem is complex, the power of parallel computing, the effectiveness of optimization algorithms, and online databases, make it possible to solve it in the Industry 4.0 environment. This problem can be solved on MSD computers in vehicles. Finally, there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972. In the book Human Problem Solving wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.